In the last video, we talked about infrared spectroscopy. In this video, we're going to talk about photoelectron spectroscopy. Photoelectron spectroscopy is the technique that lets us determine the energy levels of molecular orbitals, as well as insight into whether they are bonding, non-bonding, or anti-bonding. So what is photoelectron spectroscopy? Well, it's based on a principle that you ought to be familiar with from Chem 1000, which was the photoelectric effect. In Chem 1000, when we talked about the photoelectric effect, we were analyzing metals, but other than the fact that we're now going to be looking at molecules instead of metallic samples, the principles are the same. We're going to start off by striking the sample with light. And if that light has enough energy, it will excite an electron out of the molecule. We are able to measure the kinetic energy of the electron ejected from the molecule. And if we know what the energy was of the light that struck it in the first place, and what the energy is of the electron that got kicked out, then we know that the difference between those two quantities of energy must be the energy that was required to eject the electron from the molecule. So we can therefore calculate the energy of the orbital that the electron was in. So if, for example, we had some sort of diatomic, let's call it X2, then we're going to strike it with light, and that's going to give us the resulting cation and an electron whose energy we can measure. So we can measure the kinetic energy there. We know that the energy of the light is going to be equal to the ionization energy, the energy of that orbital that the electron was initially in, or more accurately, the difference between 0 and the energy of that orbital that the electron was in. So, in other words, the absolute value of the energy of the orbital, plus the kinetic energy of the ejected electron. And so that's the process by which all of this experimental data is achieved. This is the instrument that does that, or at least it's a schematic of it. And you can see, again, we have our sample in here, which has been vaporized to make it gaseous. Light comes in and hits it, ejects electrons, and so the electrons are going to come out. They will then get passed through the analytical system and over to the detector. Now, the wavelengths of energy that actually eject an electron completely out of a molecule tend to be ultraviolet. It usually takes more energy than just visible light in order to do that. And so this experimental apparatus is often called a UPES, for ultraviolet photoelectron spectroscopy. I'm just going to stick to talking about photoelectron spectroscopy in general, rather than adding the word ultraviolet at the front every time I need to say the word. What you get out of that instrument is something that might look like this. Now, this is the result that you would get from analyzing a sample of neon gas. Neon is, of course, an atom. It's not a molecule, meaning it has no vibrational energy levels, because if you only have one atom, there's nothing for it to vibrate against. So this is going to be a much cleaner spectrum than every other spectrum you see, having only one line for each energy level. But I think it's still instructive. The other thing that I think is really instructive for you to recognize, just looking at this nice simple diagram for the neon sample, what you are seeing in your photoelectron spectrum can be imagined to be an energy level diagram turned on its side. What do I mean by that? Well, let's look. We have neon. If I was to draw the energy, or the valence energy diagram for neon, I'd have something that looks like this. because it's 1s2, which is core, and therefore too low in energy to show up unless we used a really high energy form of light. It's very difficult to excite a core electron out of anything. So we're seeing our valence electrons usually, because they're the ones that you can actually excite out with usable wavelengths of energy. And we are able to excite 2s electrons out of this atom. We are able to excite 2p electrons out of this atom. If I take that diagram and I turn it on its side and I draw it here, trying to draw sideways on a computer is interesting, then I might have something that looked like this. And attempting to draw electrons sideways, even more interesting than attempting to draw normal orbitals, empty orbitals sideways. But there's my diagram I had over here, rotated 90 degrees and drawn above my spectrum. Why did I do that? So that you can see that what this spectrum is showing you is the energy of the 2p, the energy of the 2s, and this point up here, this 0 line, well, that there is our 0 point, the point at which if the electron is excited beyond that, it's not in the atom anymore. And every time you look at a photoelectron spectrum, I think in all honesty, your best strategy is to imagine it as, in this case, an atomic orbital energy level diagram turned sideways, but in most cases, a molecular orbital energy diagram turned sideways. Or if it's easier, turn a photoelectron diagram sideways and put it next to your MO diagram. So on this page, we're going to look at the photoelectron spectrum for a molecule. Quite a simple molecule. We're looking at diatomic hydrogen, but this will show you how those vibrations fit in. So what we see first is we see the potential energy curve for the bond in hydrogen. Up here, I'm going to draw out or sketch out the middle portion of my molecular orbital energy level diagram for hydrogen. You remember there was a 1 sigma MO that was bonding and a 2 sigma star that was anti-bonding, and we had 2 electrons in there, so 2 electrons, there you go. If I take my diatomic hydrogen and I excite an electron out of there to make H2+, can't really draw the Lewis diagram for that very well, so I'm just going to write H2+. What is the MO diagram going to look like? Well, I have my 1 sigma again, I have my 2 sigma star. Those energies have changed a little bit due to loss of an electron, but their relative positions are the same. I kicked an electron completely out. So now my MO diagram looks like this. So over here, I had a bond order of 1, a single bond. Over here, I have a bond order of a half. So my potential energy curve has gotten broader, and you can see that here. You can see that we had a sharper curve when my bond order was 1, and now we have a more flattened out curve now that the bond order is a half. So we've changed the shape of the potential energy curve. Now, to excite the electron out, as you can see, we changed the energy. We won't necessarily immediately hit the ideal bond length. In fact, we won't hit the ideal bond length just by kicking an electron out, because our bond order has reduced. So our ideal or average bond length has lengthened. So that means that when you initially excite that electron out, you take your molecule not only into the cation form, but an excited state of the cation form. And then from there, it has to relax back down to the ground state of the cation form. So that means that your signal on your photoelectron spectrum is going to look like this. It's no longer one neat, clean line. It's not just the one peak and that's it, that's all. It's a whole bunch of peaks, because depending on the exact bond length that your bond happened to have at the point in the vibration where the electron was kicked out, and where that fell on the vibrational energy spectrum for the higher energy, the cation form, and how much it had to relax, you have a lot of different options. So you get what we call vibrational splitting of the peak. And it's important to understand that when you see all those little lines together, it's one signal, and what you're seeing is just vibrational splitting. Now, the distance between those lines in the vibrational splitting is what we actually use to tell us if we have ejected an electron from a bonding or an anti-bonding or a non-bonding electron, because doing each of those things does something different to the average bond length and therefore the shape of the potential energy curve. So if we start with the simplest case, the non-bonding electron, my potential energy diagram might have looked something like this. And if I eject a non-bonding electron from a molecule, the bond order doesn't change. We have no change to bond order. And so if I have no change to bond order, then yes, I'm going to a higher energy form because I've made the cation, but the overall shape of my potential energy curve within the limits of my artistic ability should look about the same. So we actually see very little, if any, vibrational splitting. So the peak in a photoelectron spectrum for a non-bonding orbital, for ejection of a non-bonding electron, usually just looks like a line. Peak looks like one line. Now I say that there might be a tiny little ticky tail after it, but for the most part, you know, you're pretty much looking at just one big line because your potential energy curve didn't change much in shape because your bond order didn't change much. On the other hand, if you remove an electron from a bonding molecular orbital, you are going to decrease the bond order. And if you decrease the bond order, you have a shallower curve, you have a longer average bond length, and again, within the limits of my artistic ability, that means my curve might go from looking like this to, I'm going to exaggerate this to try and make it somewhat visible, to this. There we go. That should look shallower. And the vibrational energy levels in this higher up curve that I've gone to are very closely spaced. They're very close in energy, small energy gaps. And so that means that my peak on my photoelectron spectrum is going to look like a series of very closely spaced lines. So we have narrow spaced lines, which I will attempt to draw kind of like that. On the other hand, if you eject an electron from an anti-bonding orbital, you increase the bond order. And if you increase the bond order, you get a sharper well, a deeper well, a curve in which the vibrational energy levels are more spread apart. So here we have my initial curve, hopefully looking kind of the same as the other ones did. And we're going to make something that has a really sharp energy well. I'm exaggerating for the purpose of my pictures communicating anything. And we can see that the vibrational energy levels in here would be quite spaced apart, large energy gaps. So our peak then on our photoelectron spectrum is going to have widely spaced lines. And of course, the difference between narrow and wide is always relative. So you're really only going to be able to tell that you're looking at antibonding if there's also bonding on the same spectrum, and bonding if they're antibonding on the same spectrum. And anyway, so you're going to get a set of peaks that maybe kind of looks like this. And if you saw all three of those signals on the same spectrum, you would know that the one at the top up here that's just a line, that's the non-bonding. The one in the middle here that's got a bunch of narrowly spaced line, that's the bonding. And the one down here that's got those lines all spread out, big spaces, that's your antibonding. So what does that look like in pictures that don't rely on Susan being able to draw? Well, here's some nice photoelectron spectra, courtesy, I believe, of Professor Boré and Professor Dibble. So what we're looking at here are the photoelectron spectra for diatomic oxygen and for diatomic nitrogen. I'm going to start off by filling in my electrons into my MO diagrams at the left, cribbed from a textbook, which is why they don't have the same numbering system that we do, but that's okay because we are just interested in comparing the sigmas and the pi's. So O2 has 12 valence electrons, so let's fill those in like so. N2 has 10 valence electrons, I'll fill those in over here. O2 diagram for the record, in case anyone was wondering, is missing the bottom piece of it. There's a sigma and a sigma star down there, and they've also got electrons in them. So there, now you can see your 12 and where those came from. Okay, so what are we seeing on this diagram? Well, let's look at the bottom one first because it's got a beautiful example of bonding versus anti-bonding. If I take my MO diagram of oxygen and I turn it sideways, like so, and again, Susan attempts to draw an MO diagram sideways, which is never going to go well. What we have here is we can see the upper 3 molecular orbitals in terms of energy. You can't eject electrons from the lowest energy molecular orbitals without using very large amounts of energy. And so experimentally speaking, oftentimes people will choose to only study the top few energy orbitals. So here we see these guys here. They're the ones that I'm going to be redrawing. And you can see that we've got the 2 pi star there, 2 pi star, and there were 2 of them. And then below that, we have the 1 pi, and there were 2 of those. And then below that, we had the 3 sigma, and there was 1 of those. And we don't draw the 4 sigma star. Why not? Well, it's somewhere up here with no electrons in it, so what's the point? You cannot study empty molecular orbitals with photoelectron spectroscopy because you can't eject electrons out of empty molecular orbitals. So we'll take that off. So if we compare the shapes of the peaks for the 1 pi versus the 2 pi star, you can see that those lines in the 2 pi star are much more spaced out, much bigger gaps between the lines that make up the signal compared to the 1 pi. And that's that anti-bonding versus bonding space difference. So 2 pi star is, of course, anti-bonding, and 1 pi is, of course, bonding. And the 3 sigma is also bonding, and so you can see it's also a set of relatively narrowly spaced lines. It's also very common to see the signals for pi MOs of diatomics have more lines than the sigma ones for reasons way beyond the scope of this course. So don't worry about that, but that's how we can tell that we are looking at the 2 pi star, then the 1 pi, then the 3 sigma, rather than having the 3 sigma and the 1 pi inverted. Our top diagram shows the photoelectron spectrum for nitrogen. Same thing. I can take my MO diagram, maybe I'll try it at the top and see if there's a bit more space for it there, and turn it on its side, recognizing that you can't eject an electron from an empty MO, so there's no point in drawing the 2 pi star or the 4 sigma star. They're kind of up here. 2 pi star, 4 sigma star. Then I've got my 3 sigma, and then I've got my 1 pi's, and then I've got my 2 sigma star, and then somewhere below that is my 1 sigma as well. Erase the orbitals that can't actually be seen on the spectrum. And there we go. We have our MO diagram turned sideways so that we can see what the photoelectron spectrum is telling us. Well, it's telling us that we have the specific energies of these MOs. So that's what you're seeing on this scale down here. You're seeing the ionization energies, which are in positive numbers, which represent the gap in energy between the orbital and the 0 point. And so if the ionization energy of the 3 sigma is about 1260 kilojoules per mole, for lack of a better way to read that, 1260 kilojoules per mole, then that means that the energy of the 3 sigma is about negative 1260 kilojoules per mole. And the 1 pi has a larger ionization energy, it's lower in energy, and the 2 sigma has an even larger ionization energy, it's even lower in energy, and that's what we're seeing on this diagram. Because everything's bonding, we don't have that frame of reference to compare widely spaced versus narrowly spaced the way we did for the diatomic oxygen diagram. And in fact, the shapes of the 3 sigma and the 2 sigma, because they're so narrow, because it almost looks like just one line, leads us to question whether these might not, in fact, actually both be non-bonding molecular orbitals rather than the bonding molecular orbitals that we thought they were and assumed they were building the diagram from scratch. And this is why I said earlier on that we really need spectroscopic evidence to answer those questions conclusively. Otherwise, we can make our best guess and we can answer questions based on what we think seems reasonable, and that is fine if you don't have spectroscopic evidence and you're answering a question in this course. Pick something reasonable and go with it and be consistent. But as soon as you get spectroscopic evidence, it wins. Experimental evidence always beats theoretical predictions. And I emphasize that because at one point, one of the textbooks that we were using claimed that the order of the MOs for carbon monoxide was different from the order for nitrogen, even though experimental evidence suggested otherwise. And that's poppycock. You can't have theoretical predictions trump experimental evidence. Theoretical predictions never trump experimental evidence. As long as the experiment was done properly, experimental evidence wins. It confirms theories. It disproves theories. You don't get to say that the theory beats the evidence. That is bad science, and they did fix that in a later edition. And what you're seeing here is the experimental evidence that was saying that carbon monoxide and nitrogen gas have their molecular orbitals in the same order. So we see over on the left, again, the partial MO diagram, just the MOs made from the p orbitals. For both of those, if I wanted to fill in the S portion of those MO diagrams, that would come in down here. And there would be another 2 boxes here, the 1 sigma and the 2 sigma. And we would have, actually, I'm not going to draw the atomic orbital electrons because they're different for N2 versus CO, but they both have 10 valence electrons in the molecule. And so if I fill those in, you can see that what we have is the 3 sigma here for both of those, the 1 pi here for both of those, and the 2 sigma, which I had to draw in my S's to get to see, for both of those. Now you may also remember that I said when we were building up our carbon monoxide diagram and then answering some questions about it, that there was actually some evidence that suggested that the 3 sigma might have some non-bonding character to it. And this is the evidence. That is one line. And that suggests that the 3 sigma probably has some non-bonding character or is relatively non-bonding, whereas the 2 sigma over here, you can see, has lines that are spaced about equally to the 1 pi, so maybe that is actually bonding, contrary to our initial guess. And that is how you use experimental evidence from photoelectron spectroscopy to confirm or deny the predictions that you made when building your molecular